This is the second video on nonlinear systems. And here we're looking at global planar dynamics. So that's dynamics in a plane in that case. So we are looking so we'll be focusing on geometry of 2D flows. This lesson studies qualitative behavior of two-dimensional autonomous systems. And the main topics we'll be looking at will be things like limit cycles, Poincaré maps, Bendixson theorem, Dulac's criterion, global phase portrait, and structural stability in two dimensions. So straight to the talk about planar dynamical systems. A planar autonomous system has the form x dot equals f of x comma y dot equals g of x comma y. Or in vector form, we can just say x dot is equal to f of x. Of course, so the whole x thing means you're talking about you have x dot y dot into all this f and g kind of thing, where x will be x is xy and f are the functions fg. So each initial condition defines a unique trajectory. So every initial condition you have defines a unique trajectory. Then we have phase plane and flow. So the xy plane is called the phase plane. All right. So anything you have in the xy plane is a phase plane. Then the properties are each point represent a state. Every point you have there, like you say 1, comma 5, that represents a state. Minus 5, comma 7, that represents a plane. And then we see that curves represent solutions and arrows indicate direction of time. So we see that a flow maps a function phi of t. If a flow maps r squared to r squared, basically, it maps two dimension to two dimension, where phi of t x naught is the solution at time t, like that. So imagine this saddle system. Consider x dot is x, y dot is minus 1. Why is it a saddle? Because if you form the Jacobian, that is 1, 0, 0, minus 1. So, and the eigenvalues are 1 and minus 1. So that's definitely a saddle because you have an unstable manifold along the x-axis and a stable manifold along the y-axis. And then the solutions, of course, we just straight up be x dot equals x naught e raised power t, xt equals x naught e raised power t, y naught e raised power minus t. So the origin is simply a saddle point in that case. All right. So we can just write a code to take care of that. So saddle face portrait. So yeah, we're talking about face portrait. So you're going to see how arrows behave in the XY plane. Okay, so you have, of course, import number as MP. We need that here. You need matplotlib for .pyplot as PLT. We need that to visualize because that's what we are using for all these ones now. So for X now, we have X minus Y. So for X, you want minus 2 to 2. So we are doing minus 2 to 2 on both axes. You can always extend this, and we are dividing into 20 portions. And then for XY now, you have a mesh grid for X and Y so that UV can then be f of X comma Y, as you already know. Then you do a stream plot. So you need a stream plot of X and Y to show how all the arrows can behave in this case. So I click on that and I try to run that so we can see the saddle face portrait because of course from the eigenvalue we know that we have a saddle. We have one is positive, the other is negative. So we get a saddle like this with everything moving. So it's more like everything is this is the point, by the way. What are the saddles now? There we got x 1 minus 1. But of course, the equilibrium points are 0, 0, right? If you equate x to 0 and minus y to 0, you get 0, 0. So the equilibrium point is 0, 0. But that equilibrium point 0, 0 is a saddle because the eigenvalues are 1 and minus 1. So this is the equilibrium point, but it's a saddle. And that's why it looks like things are coming, but when they come, they move away. Everything comes instead of sinking into it, instead of it being a sink, it's a saddle. So everything it's coming, but then they just get diverted away from it because it's a saddle point like that. So let's talk about vector fields now. A vector field is f of x comma y, which is equal the set of f of x comma y comma g of x comma y, right? And the properties are they determine a vector field determines the motion. The zeros are equilibria, smoothness implies uniqueness, and equilibria satisfy f of x comma y equals 0 and g of x comma y equals 0, which we have always known. Then we also have what we call limit cycles. Okay, a limit cycle is an isolated closed trajectory. So the properties, it's a periodic orbit, it is isolated, it attracts or repels neighbors. And then the types, you have stable, unstable, and semi-stable limit cycles. I guess I should be careful the way I use limit cycles and center interchangeably. So this is limit cycles now. So a center is a center. It's more like it's always yeah, it has an orbit around it, maybe not even periodic. All right. Yeah. So for we've seen the idea of a Van der Pol oscillator before. So it's a second order system which can be broken down into two first order systems where we can say x dot is y and y dot is mu into all of this. So for mu greater than zero now. So if you take mu is a very good parameter. So for mu greater than zero, we can see that the origin is unstable and a stable limit cycle thus exists. So I mean, it has a very nice, a very interesting behavior. In fact, you can even draw artistic inspiration from a Van der Pol simulation. So imagine, so here you need NumPy, you need the matplotlib, then you need to integrate the system because you are solving a two-dimensional system now. So of course you may want to find the equilibrium point. For instance, I can already see here that y can be zero. If y is zero, this goes, everything here is gone, and then we have x to be zero too. So it's more like the equilibrium point is zero, zero. So it means in this case now we most likely have a limit cycle around, hovering around zero. So this is what we have right here. So you can see zero zero is somewhere here, right? Zero zero is somewhere around there. So you have a cycle around this is the Van der Pol limit cycle now. You have it around zero zero, which is the equilibrium point somewhere here. Okay, what if we change this to say two? What happens? I'm not sure. Let me check. So if we change it to two, okay, the edges become sharper. So let me see. Let me try to push limits. So if you want to understand behavior, sometimes you need to. Okay, now the more you push it, the sharper it gets. Okay, what if I do 0.2? What does that give us? 0.2 like this. So, it's more like you want to see, yeah. So, okay, the smaller it gets, the more it becomes like, so it's like you have the edge getting sharper and sharper as mu becomes bigger and bigger. What if I do 0.02? Does it give any shape? Okay, the tinier it gets, the more it's looking like an ellipse, but the bigger it gets, it's shape. So whatever is happening, right? It is, that orbit, you have a kind of orbit being maintained. Okay, let me even push things go further. Okay, so it's still looking elliptic in nature. So, but then if we take mu to be 1.0, which was the default thing, we have this now. Okay, so we have this kind of thing. All right, so that we then talk about the Poincaré's maps. So if you choose the transversal section sigma, define the Poincaré map P, which maps sigma to sigma. So that's it maps the transversal section to the transversal section. Then P of X can then be the next intersection, and then we have fixed points where P of X is equal to X, corresponding to periodic orbits, right? So stability now can be decided like this: the absolute value of P prime of X less than 1 means you have a stable cycle. So if the absolute value of p prime of x is less than 1, you have a stable cycle. Otherwise, it is not stable. So imagine here now, we have x is solution dot y of 0, y is solution dot y of 1, and then we have the crossings now. So for I in range 1 to length of x, so we have the crossing appendix and all of these things. And then we can have the Poincaré map. So more like when you have, so that's the fixed points p of x equals x there. So we just have these points scattered all over the place, like all these ones now. So that shows us the Poincaré map for Yn. You have this 2.182 to 2.196. Same on this side. And so you have Yn here to Yn plus 1, like that. Okay. So then we talk about the Poincaré-Bendixson theorem. So if you let R be a subset of R squared, and that R is closed, it's bounded, and it is no equilibria, then it has no equilibria, then every trajectory in this R will approach an equilibrium, a periodic orbit, and a union of equilibria too. Okay, so chaos is impossible in planar autonomous systems. So this is the idea here that chaos is impossible in planar autonomous systems. So like I always do, let me look for a layman's explanation of Poincaré-Bendixson theorem. Okay. Uh, Po- Poincaré, Poincaré, Bendixson theorem. In the layman terms, if I like. Okay, so here, the Poincaré-Bendixson theorem is a fundamental concept in mathematics, specifically dynamical system that dictates how points move over time in a two-dimensional space, or what you call a plane or a surface. In layman's terms, it states that in a simple 2D system, that's when you have X and Y, right? If a moving point is trapped in a certain area and cannot escape, it must eventually settle into a predictable repeating behavior. Okay, so the key idea is that there's no chaos in two dimensions, basically. So in 2D, there's hardly chaos. So the most crucial takeaway is that in 2D, like a sheet of paper, continuous systems cannot be chaotic. They cannot behave randomly, fly off to infinity, or move in endlessly complex or non-repeating paths. So what happens in the long run? If a system is trapped in a confined space, or what you call a bounded region, the path of that system will eventually do only one of two things. Number one, it can stop moving because it lands on a fixed point. That's an equilibrium or steady state and stays there. Or it can move in a cycle. It settles into a limit cycle. I've demonstrated the idea of limit cycle a couple of times. Like you have this point, and then the system just orbits around that fixed point. That's what a limit cycle looks like. Just like what we also saw with the Van der Pol limit cycle. So the analogy is that you have the roller coaster in a canyon. Imagine a roller coaster car rolling on a frictionless hilly terrain, the 2D plane. If you're in a deep bowl-shaped canyon, you might eventually stop at the bottom, which is an equilibrium point. If you have just enough energy, you might keep cycling the bowl halfway up, repeating the same loop forever, which is a limit cycle. Because the track is a flat surface 2D, the car can never turn into a flying machine, which is chaotic, or move in a way that never repeats, which is complex, non-periodic behavior. So the key conditions, we have two dimensions only. This applies to flat planes or 2D surfaces. In 3D, like our real world, systems can absolutely be chaotic. So there's no chaos in 2D. That's the summary of the Poincaré-Bendixson theorem. So continuous and smooth, the motion cannot be sudden, jump, it cannot have sudden jumps or breaks. Then bounded region, the system must stay within a specific finite area. Why does this matter? So the Poincaré-Bendixson theorem is used in biology, chemistry, and physics to prove that a system like predator prey populations or chemical reactions will not act randomly, but will instead reach a stable population or predictable repeating cycles. So that's the point there. That in 2D, there's no chaos. So you can have uh, you know, repeat patterns that can be predictable. So Poincaré-Bendixson theorem, if you have this now, which is so we have the closeness, the boundedness, and there are no equilibria, then every trajectory in R approaches an equilibrium, a periodic orbit, or a union of equilibria. And then that shows us that chaos is not possible in planar autonomous system. That's chaos is not possible in 2D in essence. So we have the Dulac's criterion, which is the next point we're looking at. So let B of X comma Y be C1. Okay. If the grad dot BF, that's the gradient of the dot product of gradient and BF, this B we have here, and F, a field, I believe, has constant sign in D, then no closed orbits exist in D. So a special case, we have the Bendixson, where df dx plus dg dy is not equal to 0. That's a special case right there. So let's look at what the Dulac criterion means for a system like this. You have x dot to be x minus y, and y dot is x plus y. So we have the divergence. We have the dive of f. So dive of f here is equal to 2, greater than 0. So no limit cycles exist in this particular situation because this is greater than 0. Because of course we already know. So it's like we say df dx dg dx. So this is the f dx is actually 1, the g dy is equal to 1 too. So if you differentiate this with respect to x, you get 1. Differentiate this with respect to y, you also get 1. So if you add 1 plus 1, you get 2. So that simply means that no limit cycles exist. And for the idea that there is that you have the eigenvalues. Oh, okay. Maybe I think I don't have to talk about eigenvalues in that case. But I mean, this is just the deal here. Just do partial f, partial x. This is your f. And this, okay. I guess I'm talking stories, right? X dot is X minus Y. Y dot is X plus Y, right? X dot, X dot. So X dot is X, is it X plus Y? X dot is X minus Y. Y dot is X plus Y. Okay? X plus Y. X dot is X minus Y. Y dot is X plus Y. Like we said, this is F of X comma Y. Or you can simply call it F. This is G of X comma Y. And you can easily call it G. So if you do the grad dot F now, so it's more like saying D, D, so it's more like saying the F, of course, dx plus dg dy. So if you have up to a third one, right, that'll be the h dz, but we just have this now. So the f dx, so that will simply be the f dx, differentiate this with respect to x, you get 1. Differentiate this with respect to y, that's another 1. So you then have 2. Okay, you have 2, and that is greater than 0. So that means that there are no limit cycles. It means you can determine for sure whether the system is stable or not stable. So that's what the Bendixson Dulac's criterion gives to us. So just do partial f partial g plus partial g partial y plus partial h partial z if that exists, and so we can do the divergence computation here now. You have x, y are the symbols here. So you have f to be x minus y and g is x plus y. So you do the div of that and you see. So I mean you're going to get 1 from here and get 1 from here too, basically. Like all I just did. So I just going to get 2. So that means that that's the divergence computation. You do that here and then that's just what you get, like that. So, and of course, that's what I also computed on that side. And that shows that there's no limit cycles exist in that case. Okay, so um we move on to global phase portraits. A global phase portrait shows all equilibria, limit cycles, separatrices, asymptotic behavior. Asymptotic behavior is that thing where you see in saddle where something is moving towards the equilibrium point, but very close to it, it just gets diverted away. Okay. Then you have construction steps. You find equilibria, you linearize, you classify. Linearization is about the Jacobian part, right? Where you form the Jacobian matrix and then you find the eigenvalues and then you classify the equilibria, and then you can use global theorems and sketch trajectories. So imagine how do you go about the global portrait for a system like this? So here you have x dot is y and y dot is x minus x cube, right? The equilibria are simply 0, 0 and plus 1, plus or minus 1 comma 0. What are we saying? When you equate this to 0, okay, maybe I should do that too. X dot is y dot is x minus x cube. Okay, x dot is equal to y, and y dot is x minus x cube. So first thing you do is find equilibrium points, find equilibria if you like, find equilibria. What does that mean? That means x dot is equal to 0. That implies that y is equal to 0. Okay, this is clearly that y is 0, settled. Then for the other one, y dot is also 0. Still talking about equilibria, y dot is equal to 0. That also implies that x minus x cube is equal to 0. So how do you do this? You factorize x into 1 minus x squared is equal to 0. So that means you have x into 1 minus x into 1 plus x is equal to 0. So you have x is 0. From here, x is 1. I mean, yeah, x is 1. From here, x is minus 1. So what do you get? So you can then pair up this y equals 0 with all these points now. So equilibria here, you know, take this 0 and that 0 for y, then the next one, you can take 0 with minus with 1, if you like, anyhow you want it. 0 and 1, then you have 0 and minus 1. So in all, that's why what you have there is, uh, you know, all the x's. No, 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 no. This is not what I should be doing. Sorry. the y is at 0. So for the first one, x is 0, y is 0. For the next one, x is 1, y is 0. For the next one, x is minus 1, y is 0. Yeah, that's the deal. And that's why this one is summarized into 0, 0, and then plus or minus 1, comma 0, like that. Y is 0, confirmed, So these are the possibilities here. Then, of course, you may also want to do a Jacobian for this now. So if we want to do the Jacobian for that, right? Again, we have the system x dot is y, all right? X dot is equal to y, and y dot is x minus x cube. Okay, so to do the Jacobian in x comma y, so we have that means we have differentiate this with respect to x, you get 0. With respect to y, you have 1. Then y dot with respect to x, we have 1 minus x squared. With respect to y, this is 0, like this. So what do we do? Aha. So you now have to evaluate this Jacobian for every equilibrium point, one after the other. Okay. So you can then say you can then do one after the other. So at j 0, 0, okay, let me change this all together. So at j 0, comma 0, that's the first equilibrium point, So it means you have 0, 1. So if you put 0 here, you have 1, 0. So you can then find the determinant for this one. So by now we already know this is the determinant of J, rather eigenvalues like lambda 1. Okay, well, to find eigenvalues, right, we have what am I? Okay, it looks like I have to keep following the stuff. So determinant of this minus lambda I now. This is simply 0 minus lambda. This is minus lambda 1, 1 minus lambda like this. Okay. Yeah. And the determinant of this now is simply equal to 0. Okay. Yeah, I think this is the faster way. So for eigenvalues, we have this. So here now we have lambda squared minus 1 equals 0. So that means that lambda squared is equal to 1, of course, and it's not complicated. So that's plus or minus 1. So for this now, we have the two lambdas. You have lambda 1, lambda 2. This shows us we have a saddle. So it means that this particular 0, 0, this 0, 0 is a saddle. This is a saddle like this. Okay, well, I mean, I've set it down there. So 0, 0 gives a saddle. Then let's do the other one, which is 1, 0, okay? Plus 1 and 0. So again, we have J 1, 0. Okay, so here now, it's because we have X here now, so you have to follow what you have. So here, X is 1, Y is 0. Okay, so we have this to be 0, 1. So for 1 minus x squared, x is equal to 1 here. So we have 1 minus 1 squared, which is also 0 like this. And then that is 0 here. Okay. So to find the determinant here, so we have the determinant of minus lambda 1, 0 minus lambda, okay, and that is equal to 0. So that means you have lambda squared. Lambda squared equals 0 in short. So lambda squared equals 0 simply means we have lambda squared equals 0 means we have lambda to be 0, and that is actually, this is a center, okay? This is a center because the determinant is 0. That gives us a center. So I think we're also going to get a center for the last one, which is minus 1. We are going to get a center for minus 1, 0, 2, because if we put minus 1 square, if you square minus 1, you get 1, 2. So again, if you have j into 1, 0, no, j into minus 1, 0, right? J into minus 1, comma 0. This is, again, the matrix is 0, 1, 1 minus x squared. So 0, 1, 1 minus 1 squared. Then this is 0, right? Yeah, I think that's what we have. Yeah. So 1 minus 1 squared is 1. So minus 1 squared is 1. 1 minus 1 is 0. Okay. And it's exactly the other thing, what we did there before. So this is the determinant of minus lambda 1, 0 minus lambda, equals 0. So that's simply lambda squared equals 0. So lambda is simply equal to 0. Again, we have a center. Okay. That's what we have in that case. So that's how the whole thing goes. So we have two centers and one saddle. Okay, so that's how to determine the global portrait of a system like this. So this thing we have said now, we are plotting that we have we want to return y and x minus x cubed like this. So that's the first one. X dot is y dot is x minus x cubed. We are defining the function x comma y like this here. So we have mesh minus 2 to 2 minus 2 to 2. Of course, we already know that the equilibrium points are 0, 0, 1, 0, and minus 1, 0. So this minus 2 to 2 will capture everything very well. Then we do the mesh grid xy, mesh grid for x comma y, and UV we have f2 xy. Then we do a stream plot to see how the arrows go. So we see 0, 1, minus 1. For scatter, we do 0, 1, minus 1. So because we actually want to see this point, 0, 0, 1, 0, minus 1, 0. We want to see all this. And then we now see the global phase portrait based on all the analysis we have done. And then, okay, I mean, we get this beautiful portrait right here. So you can see that this is 0, 0, which is a saddle. So you see everything is coming and then it's diverted. And this one is coming, it's diverted. But then minus 1, 0 is a center. So you can see everything is cycling around it. Then the 1, 0 is also a center. You have all the streams are flowing around it. So it's flowing around, it never gets to it. And this one, it's coming close, but then it gets diverted when it gets too close. So that's the global phase portrait like that. And then let's talk about structural stability. A system is structurally stable if small perturbations do not change its qualitative behavior. So two systems that are topologically equivalent if trajectories correspond via a homeomorphism. Okay, one way I like to think about stability is this. There are all kinds of stability, right? So imagine if okay, maybe I should imagine a ridge, right? You have a ridge. Imagine you have a ridge like this. So, if you balance a ball here, okay? If you balance a ball on this ridge, so imagine that you now balance a ball on this ridge. So you have this ball here. So it looks stable, right? But if you push it a bit, if you push the ball, it will end up coming into this place. Now, but if you push the ball, if you try, so if you push the ball a little bit up here, in this case now, it will always come back down. Okay. If you push it up a bit here, it will always come back down. So what we are simply saying is that, so if you look at this place, the ball here, even if it is stable, it is how do we say it? This so it is unstable equilibrium, right? Even if it is in equilibrium, it is unstable, and here it is stable. Okay. I don't know if that's a very good example, but you understand at this point, if you push it a little bit, it simply goes it goes down. And when it comes down, it's hard to push it out, except you apply so much force. Okay. So and for structural stability, we're talking about uh small perturbation not changing the qualitative behavior of a system. Then we have the Peixoto's theorem for a plane. So on compact sets, right, a planar system is structurally stable if and only if and only if it has finite equilibria and cycles, all equilibria are hyperbolic, and then no saddle connections and no degenerate cycles. So no saddle, no degenerate, and then you have equilibria that are finite, and then all are hyperbolic. So for a composite, that's Peixoto's theorem like that. Then we talk about hyperbolicity. Of course, we've made mention of that already. An equilibrium is hyperbolic if the real number part of the eigenvalue is not equal to zero. So if it is equal to zero, then it is non-hyperbolic. So, and that happens for all eigenvalues. If you have 10 eigenvalues and one of them has a real a zero imaginary a zero real part, then it breaks. So you can then say this that particular equilibrium is not hyperbolic, and then it disrupts the whole thing. So in this case, hyperbolic equilibria persist under perturbation. Hyperbolic equilibria persist under perturbation. So a stable system remains unstable and a stable system remains stable even under perturbation, right? So examples of stability. Now you have x dot is minus x, y dot is minus y. Of course, this is clear. The Jacobian will be minus 1, 0, 0, minus 1. So the eigenvalues are minus 1 and minus 1. So this is clearly stable. And then this is unstable because x dot is y dot is 0. Okay, if you form the Jacobian, you have 0, 1, 0, 0. Okay, so in that case, there's zero eigenvalue, and that implies instability when you have zero eigenvalue. So we can demonstrate that here with, so for the first one, we have minus x, and for the second one, we have y0 or something like that. So in this case now, okay, this zero, instead of just putting it there, because we want to do y and x, so you need to fix that with x right here, so you can have something reasonable to plot. So we run this down, we show this, we show the stable case and we show the unstable case. Yeah, look at them. For the stable node now, of course, if you look at the system, the equilibrium, if you equate minus x to 0 minus y to 0, you get x is 0 and y is 0. So we have, that's the only equilibrium point. But then the eigenvalues are minus and minus 1. That means you have a stable equilibrium. Whereas on this, in this other case, you have instability like that. So in this case now, so look at this. So 0, 0 is stable because you have all the streams flowing into it. But in a manner of speaking, you have all the streams flowing into it. So it's a stable node. But for the non-hyperbolic system, you just have everything flowing like that. Like it's not flowing towards any particular direction. Everything is just going the way it's going. So one thing we have noticed is that if you want to do this kind of thing, you need to do a stream plot. That's what you do here using Python like that. So this, you see a hyperbolic system behaving, there's no clear direction, but here everything is moving towards a particular node. And if it was unstable, everything will be moving out like that. In fact, I can even change something here. What if I change this now? If I change y to minus, to plus rather, and x remains minus, it's no longer stable. It's now see this point becomes a saddle automatically. So 0, 0 is still the equilibrium, but every arrow is moving away from it. Then what if I change both? Like x now is also positive. Okay, if x is positive now, we have an instability. So everything is flowing out of 0, 0. It's now a source. So minus minus, it's a sink. Minus plus, it's a saddle. Plus plus, it's a source. Everything flows out of it. So you can see stability in terms of that kind of thinking, that minus minus, you have stability. That means everything is flowing into the system. Okay, I've not run this now after changing it. So minus minus means you have everything flowing into the system. In that case, it's a sink. Plus plus means everything is flowing out of the system. In that case, it's a source. Then minus plus means confusion. So it's trying to flow there, but it doesn't ever get there. That's the idea. So in summary, we have that we have geometry. Geometry shows us the flow structure. Limit cycles talks about periodic orbits. Poincaré map talks about discretion reduction, and PB theorem, that's a Poincaré Bendixson theorem, talks about limit sets. That there's no chaos in two dimensions. Then Dulac gives us possibility of exclusion, like excluding cycles, right? Yeah, centers, yeah. Then for you have portraits. Portraits give you a global view, and I demonstrated the process of getting that global view. So you get the equilibrium points possible, and then you linearize, you get the Jacobian matrix, right? Then you evaluate the Jacobian matrix at each equilibrium point to see the kind of eigenvalues they have, and then you can then see which one is a stable node, unstable node, a saddle, a maybe even a spiral, maybe a spiral sink, a spiral source, or even a center when one of the real parts of the eigenvalues, if one of the eigenvalues has a zero real part, and then stability talks about robustness, that even if there's a little bit of perturbation, you don't have any significant difference taking place. So the conceptual roadmap we've seen so far for global planar dynamics, we have local analysis, talk about the equilibrium points, and then do look at linearization and all that. Then you have invariance and Poincaré Bendixson, limit cycles, global portraits, and then we talk about structural stability. That's what we've done so far. So we have some practice problems as usual. Solve the following problems, show all steps, and justify your conclusions. Okay, so imagine we have the first two here. Equilibrium and classification. Consider the system x minus y, x plus 3y. Find all equilibria. Of course, you are going to solve this simultaneous equation. So one easy way is we can subtract x minus x gone, and then x minus y is 0, x plus 3y is 0. So x minus x will be 0, and then we have 3y plus y. That's 3y minus y equals that will be equals 0 too. So y is 0, And since y is 0, x will automatically be 0. So you can linearize the system at that point, classify each equilibrium and all of that. Then phase portrait sketching. So for the system y minus x minus y, find eigenvalues of the linearization, determine stability, sketch the phase portrait. Of course, get the equilibrium. Of course, the equilibrium here, y is 0 and x is also 0, clearly so. And then so you then linearize, you have 0, 1, minus 1, minus 1. So you find the eigenvalues and then use that to, so that will now tell you if it's the kind of point the equilibrium is. Okay. Then 3, 4, limit cycle detection. So x dot is y, and then that, I mean, to detect limit cycle, yeah, simply once we get a determinant that is equal to 0, I mean, an eigenvalue that is equal to 0, then you know a limit cycle does exist. So you want to check that out. Then Dulac's criterion. So you do differentiate this with respect to x. I mean, I think that can be done easily. Partial f partial x, you get 1 here. Partial f partial y, you get here. 1 plus 2 is 3. So there's no limit cycle. Okay. So decide whether periodic orbits can exist. Periodic orbit cannot exist because the Dulac's criterion is 3. It's greater. Yeah, yeah. Okay, yes. This partial x, this partial y, partial f, partial x, partial g, partial y. Yeah, it's 3. So then 5 and 6, we have Van der Pol analysis. Consider the Van der Pol, find equilibrium. I mean, we've done this before. 6, Poincaré, same. Then 7, Poincaré Bendixson application. Let R be a closed bounded region containing no equilibrium. Assume all trajectories enter R. State Poincaré Bendixson. It simply tells us that when something is trapped there, it either rests or it takes a shape, that a pattern, it takes up a behavior that is well understood, that can be understood, right? Because there's no chaos in 2 dimensions. That's the import of the Poincaré-Bendixson application. And we have the global phase portrait, of course. Find equilibria that just solve simultaneously. I can already see x is 0, y is 0. Then you can solve this other one simultaneously and you get more points. Like, I think overall you should be able to get like 4 equilibrium points. And find equilibria, classify it, draw a global phase portrait, can do all that. Then for 19, we have structural stability. X dot is y dot is minus x plus epsilon y. Find eigenvalues, just, of course, y is clearly 0, x will also be 0. Determine for which epsilon the system is hyperbolic. Of course, okay, I mean, you have to form the Jacobian and you have to set it in such a way that you have a non-zero eigenvalue based on the epsilon. So that's possible. Then bifurcation and stability. Consider this. X dot is this and y dot is that. Find equilibrium as lambda varies. For varying lambda, it's sure that y is 0. But in this case, now you can have some behavior here based on the varying lambda. Then classify stability, describe changes in the phase portrait. So with this, I come to the very end of this interesting video about global planar dynamics. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, the question is, what exactly are you waiting for? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you some special privileges, like we can hang out together to discuss anything that interests you on this channel, you know, all kinds of things. So look at the perks like that. Ultimately, you can comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.